All right, thank you for showing up for my presentation. So I'll start with, you know, so the idea of title is interesting, right? So why I named it like a tale of two cities. Basically, we have two ways of dealing with concurrency nowadays, right? One is pretty much blocking. We just write imperative way of programming, and the other is basically we try to invent a new framework like reactive or asynchronous way of dealing things, right? We do a lot of invention in that area. So that's a two way of doing things. So basically, I'll start with some background history so that you can relate how it improved and where we are now. Anyway, so what happened? You can see, right? Okay. Sorry for this struggle. I'm struggling a bit over here. But anyway, so that's basically my agenda. I'll try to give you an introductory basics and history a bit of history, and then finally I'll talk a bit about Project Loom that's recently we are getting introduced, and JDK 21 will get that. So it's available for to try. It's been from JDK 19 on a preview feature, and finally in JDK 21 we're gonna get it as a without preview feature. Basically, we will be able to use in production. So I'll touch that at the end. All right, so I'll start with context and history. All right, I guess pretty much everyone knows that from the day zero Java introduced thread. That's the one of the reasons why Java is popular. Do you have any different thought process? Like, do you know that this is not the reason why Java is popular? Can anyone share why Java is popular? Definitely, that's one of the reason. Personally, I feel that's the reason why Java is popular, because it introduced thread. Back then, no other programming language had this capability of creating threads on an ad hoc basis. So yeah, definitely some other aspect of Java of being popular, but this is one of the reason. Anyway, so the question gets to be why we need a thread, basically. Basically, what we want is we want an execution environment where we can put our code and it will run. So idea is if we have more thread, that means we will have more execution environment. So that Java basically gives us that, and the benefit is plenty, right? We can simultaneously do a lot of work together. So that's the idea. Anyway, moving on. And if you see Java ecosystem, it's all layer in all layer thread is used. It's be it exceptions, thread locals, debugger profile, whatever you think and internally, it's pretty much used by the threading mechanism used heavily. Even though if you write a simple program that has a hello world program, right, like this, it doesn't have anything at all, but still you are basically using threads, because it's this code from the first curly brace to last curly brace, it's going to be executed by a thread, which is main thread. All right, so moving on. Now the question gets to be, how do we create threads? That's a simple code. You will create a new thread, and inside this curly brackets, whatever code you put, it's going to be executed by a different execution environment. So we can have multiple. All right. So we have to keep one thing in mind. I don't know if you can see it, but the idea is if you take the thread drum, you will see Java doesn't have a concept of thread. Basically, it's not a JVM things, it's more of a OS things. Basically, thread is managed by operating system. So Java is basically a thin wrapper on top of the, what operating system provides us. So when we create threads, we basically request the operating system to give us a thread. So if you take a thread dump, you will see two kind of ID, and one is basically JVM ID, given by JVM, and the other is basically, there is called NID or native ID, whatever you can call. So they're basically, what it means is basically in Java, we don't create basically we don't manage threads. Java is a basically thin wrapper, we just send a request. Anyway, so what it gives us that is it becomes it is a expensive resource. So it takes if we want to create ad hoc basis, it takes time. It also create a 2 megabyte of it requires 2 megabyte of memory outside of heap, right? So we cannot have a lot of them, right? For example, if you want to have millions of them, we'll probably need 2 terabytes of memory. It's a huge memory. But so now question gets to be, what do we need this many of threads? I'll get to that in a minute. All right, so moving on. Give me a second. So our modern web applications basically works this way. We want to get more throughputs, right? We want to do more things with the web application. So let's say, think about a simple web application. Let's say Twitter, right? We want to send as many requests as we want, and when we send a request internally in the server, what happens is this request is handled by a particular thread. So, and then it works internally. It goes to the database or other third-party service if required, and then getting all this information, it accumulates the data and then send back to the client. It's all done by one particular thread, right? So that means if we have a limitation of threads, we will not be able to have as many requests as we want, right? So we have a sort of limitation over here. So that's what it is basically. Our modern applications, web applications, are sort of, our throughput are limited by the number of threads we can have. So that's the problem currently we are having. But if we had more, threads, for example, if we had 1 million threads, we can, arguably, theoretically prove that we can have more throughputs, because our modern operating system can handle millions of requests, right? And if we had millions of threads, that means our throughput will be skyrocket, right? That means we would be able to, handle so many requests so that's the idea. But that's a problem currently we have. We cannot have that. So I'll get to that in a minute. So basically, if you run this code in your computer, what it does is it's in a loop. It just keeps on creating threads. After a while, you will see you will no longer be able to create threads. So you will go with something like unable to create memory, something like that. Have you experienced this kind of situation when you want to create threads, but yeah. So basically that's a problem, right? I mean, we started our application, and for some reason, let's say we want to create ad hoc basis a lot of threads. Whenever a new request comes, we want to create a new threads, and after a while, application will just stop. It will crash because we are not able to create any more threads. So these are problem, right? These are the existing problem we had, and we kind of solved this kind of problem in many different ways. I will come to this. But the idea is from this, from over here, the takeaway is we cannot create as many threads we want. And if we could, we'll have a lot of benefits. So we sort of, go way around and invent a lot of interesting stuff. I'll come to that. Anyway, so these are some of the problems that we're dealing right now. Because our requirement of modern application increased. We have a lot more need to deal with a huge set of data. The requirement of throughputs are way higher than earlier. Like in early days, we probably didn't have that many capabilities, but now we need more capable systems, right? So these are the kind of problems we are dealing. Now, problem is, we established the fact that thread is an expensive resource, and we have a limited number of that. And the throughput is kind of determined by number of threads we have. So now, on top of that, some of those threads, if blocks for doing nothing, what would happen? So let's say I have 100 threads in our system, and on those 100 threads, most of them, they are basically stay idle. They don't do anything. They wait for something to come. So let's say you want to call a third-party service, a microservice, from a particular thread, and it's a third-party service, right? There is a round, latency there. So while it's waiting for the data, thread basically is waiting, right? So it is blocked. This thread doesn't do anything else. So while doing that, this thread is basically wasting our resources. So that's why we call blocking calls, but blocking code is bad because it's basically waste our CPU. So what I'm trying to establish from this is, one thing is basically we have limited number of threads, and we have we have more requirement of capable systems, but then again our threads pretty much waste a lot of times. I have a picture, something like that. It's a basically our common server fan out. Basically, the idea is we have got a request, and there is a request handler, and request handler goes to a different direction, right? So now, let's say the first block, and this one basically, handled by one particular thread. And it goes to database, it goes to some other places, and then unless they come back, this thread basically waiting to get those results. So it's wasting basically resources. So that's what happens. And in general, if you see, this is something what happens inside a thread. Traditional applications, basically, right? So most of only few time it process, and most of the time it basically wait to get result. So from this, what we can conclude is basically blocking calls or something like is our enemy. We have to figure out something else so that our thread spend less time waiting and doing more things. So that's a resource utilization, right? If we have 100 threads and all of them are always working, that means that's a best resource utilization. Make sense? All right. So let's say we have an example, something like that. We need to calculate a credit of a person. So we have over here 5 calls, right? First one is pull the person information, get the asset, get the liabilities, and do something in between, and then calculate the credits. So all of them are basically sequential operation. So let's say main thread call this method, calculate credit, and then basically it waits until all of them get back. So in terms of it also takes time, right? Some of them could be parallelized, right? For example, after first call, the get asset and get liabilities can be done parallel, and that will get some what do we say, improvement over here. So we'll work on that. Something like that. Basically, if we run sequentially, we'll have something like, let's say every call takes 20 milliseconds. To complete this whole method, we'll probably end up getting thousands milliseconds. On the other hand, if some of the work is done, parallelly, we'll have some improvement over here. So back in the day, like earlier in the Java ecosystem, before Java 5, 1.5, that was it was called 1.5. Now the dot is removed. It's just 19, 20, 21. Anyway, before Java 1.5, something like this was created, which is called atomic references. So I'm gonna show you how this works. The idea is we can create ad hoc basis, thread ad hoc basis, and then when result is available, we'll put that into a atomic reference. So we can rewrite this earlier application like this. I'll give you 1 moment to read this code so that you can you can quite grasp it. So if I run this code, ideally the earlier I have shown an image, right? Something like that. The left side happens. So we get some improvement. So this is the code. Do you see any problem over here? So basically what happens over here is we are creating threads on an ad hoc basis. So that means if we have more requests coming in our system, we're going to create a lot of threads. And after a while, we'll get the, we'll cross the limit of our boundary, right? And application will crash again. So let's improve that. So improving is basically Java 5 introduced executors, which is basically thread pools, right? So the idea is we'll create a thread pool, bunch of thread will reside on this thread, and whenever we need a thread, we'll just submit tasks to this thread pool, and they will this task will be done one of this thread inside this thread pool, and that's how we got something like future, callable, all those things, and we can rewrite this whole things like this. We have a thread pool over here. And the first one is basically obvious. We call this, and then the second two are the second, third, and fourth. We can basically parallelize using the submitting this task to a thread pool, and when they are available. For example, and finally we can call this a asset.get and libraries.get. Obviously, this is a blocking call. That's a problem, but it gets some improvement. We are not there yet, but still we get some improvement over here. So this is how traditional thread pool looks like. I don't know if you can read all of this, but the idea is we have a thread pool, and we have a lot of threads over here. Maybe we can fine tune them, 100, 200, 1,000. Depends on the kind of work I'm doing. And what happens is basically, let's say we have a main thread over here. It starts, and then I call the get person, and then immediately I submit the next task to thread pool. So it's working over here. While it's working, it gives a reference, which is basically asset futures, and I can continue. The main thread is continuing working on. It's not waiting for getting the result. And when we need it, we can call this get method. But in between, we can improve some things. We can continue working on something. Basically, that's the idea. Anyway, moving on. So these are improvement, but we are still blocking our code. Whenever we need the data, we call the blocking get call. And probably by now we know a lot of reactive stuff, composability, a lot of interesting stuff that we want to include into our programming methodology. So there are certain problems over here. One of the problem is obviously fine-tuning the thread pool. Is it a problem or not, fine-tuning the thread pool? How many threads do we need? Do you have a magic number? We probably don't. So that's definitely a problem. Anyway, moving on. So let's improve it. We can improve some. We can keep on improving, which is Java 7 introduced a fork join pool. That's a huge improvement. Why it's a huge improvement? Because only on this there are a lot of interesting features implemented in last few couple of years. I would say last. When did Java 7 released? It's 2011, right? I forgot the date. It's around that time. And after that, a lot of interesting features were developed on top of this fork join pool. So some of them are we already familiar with. For example, reactive stuff. And the important thing about Java's fork join pool is it's really performant compared to other executors in many ways. It has work stealing algorithm. It prevents cache corruption. A lot of other interesting things. You can go in depth, but I'm going to skip it for sake of the time because I have some other things to share with you. But it's definitely a fascinating thing. The fork join pool. Anyway, moving on. So based on fork join pool, we have something called CompletableFuture. Who hasn't used CompletableFutures? Okay, and everyone else used CompletableFutures, right? Okay, interesting. So a mixed audience, but yeah, that's interesting things, and that gives us some of composability that we want. For example, the earlier code can be written something like that with the, for example, I'll give you 1 minute to read this code, and let me know if you understand this. Anyway, so what I'm gonna do is, while I'm sharing some of the background, I'm still sharing backgrounds. I'll share a lot of problems with you, the existing problem that we have. And end of the presentation, I'll show you all of these are solved by a interesting feature that's came in JDK 21, and it will be hopefully you'll enjoy that. But moving on, I'll keep on showing some problems. So do you see over here any problems? Does it? Yes, I was trying to point that basically. Let's simply focus on the readability aspect. You are an experienced programmer. Let's say you have been programming for all of your lives. Now on your team, let's say you have a new fresher or let's say junior developer comes to your team, and you want to explain this code to him or to her. Good luck with that. So that's a problem. It's similar problem with the other reactive stack. For example, I'm going to skip this slide for a minute, but there are other reactives is similar fashion available, which is Arc Java, Akka, and Vertex, Spring, Webflux, Slicks. They have similar set of problems, which is it has first of all, readability. When we write code, we have a mental makeup in our mind, right? Let's say I start a method from the first line to last line. That's how we basically compile the code on our head, right? But with this, it's crazy. You never know how the code is going inside the the way you are writing code. It's interesting. It looks interesting, and it seems we are combining a lot of things, chaining and all of those things, but we don't know how it's actually get executed. So that's a problem. And how about debugging? So yeah, extremely hard. Yeah. So the other problem is, if you want to if you want to use the reactive programming like this, all of this framework, you have to write all of your code exactly same fashion. If you introduce a blocking element in between your code, it's a problem, right? So, and it's a huge learning curve. It's difficult to debug, and some of the tools that available with the Java ecosystem, for example, debugging capabilities. It's awesome features, stack trace, all those things. Because when a thread dies or when a exception happens to a particular thread, it keeps on all these stack trace. But on a reactive step, you never know which thread run which particular things, and it's all over the place, and it's difficult to get information from the stack trace. That's a huge difficulties. Anyway, so moving on, I have a similar example with the, I have just one example over here, not all of them, because it will kill time. So that's one of the example. It's similar problem we have, which is it's difficult to read, it's difficult to debug, although we are getting some benefits out of it, right? I mean, it's performant. We are utilizing our resources best way, but again, we are also paying a lot of things as well. Anyway, moving on. I already shared with you, what are the difficulties with, reactive programming. Do you here actually, write code on reactive programming? Anyone? Okay, so pretty much I'm in a good place, right? You will not guys fight with me. Reactive programming is best. All right. Anyway, so pretty much we have a lot of difficulties so far, and all of this can be solved using one interesting thing, which is this guy. Have you tried Project Loom? Anyone? Okay, there is one. You also tried, right? Okay. So the interesting about Project Loom is, it introduced a new kind of thread called virtual thread. The idea is, although we have a limited amount of thread, which is OS handle, but we can have unlimited, theoretically, basically. And there is a limit, obviously, but theoretically we can have unlimited amount of virtual thread, which is a Java construct. It's like a lightweight task. Like you can submit a task to a thread, and it can, pretty much, you can have a unlimited amount of it. That's the first gateway. The second thing is the problem with blocking call we had earlier, right? Because thread is limited, and when we have a block, the thread gets blocked. So let's say I have 100 threads. Now 99 of them are blocked for some reason. So while they are blocked, no work is being done, right? If I have a request, let's say the limitation is 100, let's say, think about it. And all of them are busy. Now, if I get a next call, next request from a client, our application will not be able to handle that, right? Because we have, all of them are busy. But with the virtual thread, the idea is we can create a lot of them. That means whenever we need, we can just, it will just appear. And if it blocks, we don't care. How I'm going to get to that? But the idea is the virtual thread can block itself. Now, think about it. If we have unlimited source of virtual thread, and some of them are blocked, or most of them are blocked, do you have a problem? Because we can have another one whenever I need it, even they are blocked. So in a way, virtual threads are solved. Virtual thread basically solved that blocking problems. How? That's definitely we're going to discuss in a minute. But the idea is, it solves all the previous problem we had. One of the problem is, to improve our application's performance or throughput, we invent a lot of framework like, reactive programming, asynchronous way of dealing, and the difficulties of debugging, difficulties of readability, all of those basically pretty much gone. We don't have to deal with all of those things. The obvious reason is it works exactly like our traditional threads. We can write our code as imperative way, and if it blocks, we don't care. It just blocks. If we need, we'll create another one. I'll show you some demo in a minute. But so that's the idea. I have a demo over here that I'm going to show you in a minute. I have to pause this, I guess, and then I have to put my IDE back. Okay, so you can see the screen, right? So first demo that I'm going to show you is how many threads we can create with the virtual thread, first of all. Let's see. So the existing code, I didn't change any of these things. I just create a thread.start virtual thread. That's a new method available in JDK 21. If you want to try it, you can definitely try this. And if I run it, line 17. Oh, OK. Yeah, I have to, because I already started that. This method already started the virtual thread, right? So I don't have to start again. That's probably the case. So if I can, I don't know if you can read the number. So basically, it keeps on, building threads, and I don't know how long it will keep on going. Something like 8 million, right? So basically, over here, it's around 8 million threads it was able to create on this machine. I mean, probably in theory, will not create this many, but so that to show you the capabilities, it can create as many as we want. So again, so let's revisit. So initially, so when we from the first few slides, I discussed that the throughput is basically limited by the number of threads we can have. Now we have unlimited supply of threads. That means our throughput now can increase, right? We can definitely write a high throughput application with this exact similar amount of resource we had earlier. Okay. So how it works? This visible from the back? Do I have to increase size? Oh, okay. Thank you. So what happens is basically, virtual thread works something like this. There is a JDK scheduler, which is basically fork join pull, and then on this fork join pull we have some threads. It could be the number of available core you have. It could be 10, 20, 21, something like that. And then it's basically 1-1 mapping with your OS threads. That's the number of thread. And there is basically what happens is whenever you create a new virtual thread, it's basically a Java object, Java construct. It behaves like threads, but it's not the traditional OS thread. Even OS doesn't know about any of these things, which is virtual thread. It's wholly a Java construct. So what happens is when we create a virtual thread, we pass it to the JDK scheduler, which is fork join pull. The way we submit to task to fork join pull, similar fashion. Most of them are done automatically. You don't have to do anything. You just create a start virtual thread and put your task to it. And all of those things are done by internally, these JDK frameworks. So what happens is you create a virtual thread. There is a carrier thread. Carrier thread basically our traditional threads that we earlier had. And those thread takes a virtual thread and it start executing. Once it start executing and it sees a blocking operation, let's say a microservice. So that means this thread will block, right? So what happens is immediately it removes itself from the carrier thread. So it's moved back. Now the carrier thread, which is this limited number of 10 or 20, one of them is free now. So it can pick another virtual thread. And whenever this virtual thread sees a blocking operation, it just moves itself. What happens? Oh. Okay, it's back. So the idea is, our fork join pull threads are always working. They're always utilized 100%. We don't have to worry about it. Virtual threads, when it sees a blocking operation, it can yield itself from the execution. So it waits outside or waits somewhere else. And let's say I'm calling a microservice. There is a obviously latency, let's say 300 milliseconds. When the information is available, it will get its chance again. So let me give you a scenario, real life scenario. Have you gone to the bank and there is a few amount of teller, and you need to give him some information, right, to do certain things. So there is let's say there is a 5 teller, and you went to the one of them, you occupied him or her, and then you will ask some question, and then he will verify certain information, right? while he is doing all this verification, you are just standing in front of that desk, and the teller is basically doing nothing, just waiting for the information. Probably he has to, or she has to call call someone or send an email or get a fax back. You are just sitting there and occupying that amount of time. Probably to serve you, it takes like 5 to 10 minutes. All those duration, you are just there standing, and nothing's been progressed until you get all those information, right? So think about other scenario. So you go to the teller, you submit your request, and the teller will process your information, and he needs to probably get some information back. And let's say the teller needs to wait for an email. The teller will tell you, sit on this aisle. Once information available, I'll call you. While I'm waiting, I can serve another customer. So basically, the process is efficient, and now it can serve so many more customers. The whole idea is virtual 3D is about that. So idea is we have a limited number of threads, but all of them are always working. They are not, they are always busy, but they are not blocked. Because if something blocking operation happens, that particular blocking virtual thread, it goes away from the picture. The traditional carrier threads still working, serving other virtual thread, and the progress, we are making progress. So that's what happens with the virtual threads. And there are plenty of benefits with this virtual thread. First of all, while virtual threads, waiting for the, there is a blocking operation. It's yielded in waiting for something or sleeping. It doesn't consume CPU at all. It's just another object in this heap memory. And technically, we can, create millions of virtual threads. They're cheap. And again, the request per thread style, which is the traditional server-side programming, is again back. We don't have to write fancy code with reactive programming. We can just write our traditional imperative programming, which is easy to understand, easy to debug, easy to explain. We got all of them. And finally, which is extremely important, we no longer need to maintain thread pool. Who had hard time maintaining, fine-tuning the thread pool? Anyone? Yeah, it's a difficult, don't you think? So now we don't need to pull thread because we have unlimited supply. We can just create ad hoc basis. We don't need to maintain thread pools. Only thread pools that we require, which is fork join pool, it's given by JDK itself. We don't even have to worry about that. Anyway, so these are the benefits. So I'm going to show you two code and read them carefully. Let me give you 1 minute for this. OK, so next, this one. OK, so you have seen two codes, right? Just tell me which one is easier to explain and which one easier to read, and which one will have less mental work you have to do. This one is first one, which is definitely reactive programming, reactive one, and second one is basically imperative. It's a traditional for loop, nothing fancy over here. First one is A, second one is B. So who is who wants B and who wants, let's see who wants B. Pretty much everyone, I say. And so that's a benefit basically. And now you can write code like this. You don't have to learn reactive programming perhaps. I mean, I'm not against reactive programming. There are plenty of other benefits, but for this kind of things, you probably don't need to. Anyway, so there some of the frameworks still working on it. For example, Spring Boot, Helidon, Nima, Quarkus, and many other frameworks are already working on to support virtual thread. So maybe pretty soon you will be able to write your production server-side programming with virtual thread. So there is a code that I want to share with you all, which is the guy Ron Pressler, who is basically behind all this virtual thread. That's the first one, and this is the second one. And do you have any questions? That's all I have. And there is some information over here. If you can, if you want to reach me later, you can definitely, I maintain a newsletter. You can also, if you want to keep in touch with me, that's one of the way you can definitely keep in touch with me. Apart from that, let me know if you have any questions. That's so. Communication means what sort of communication you are talking about? So basically, like the traditional one you do, how traditional thread works this way. Same thing. You need to all these concurrency utilities that works for the traditional, traditional threads. You mean lock. All these things are works in virtual thread same way. Let's say you want to. There is one example. Let's say you have a resource which is limited amount, right? You want to let's say permit only 100 requests at a particular point of time, because it's a limitation. Since you have virtual thread, pretty much unlimited number of requests can get into that that particular resources. What you do use is semaphore, something like that, basically. So I think I'm almost on top of the time. So I'll just. Do you mind if I take a picture of all of you? Okay. Thank you very much.